Welcome everyone. Before we get started, I'll let you all know that we're recording today's webinar and it will be available in a few days, and you'll be able to find it on the NOAA One Health website and on the Regional Collaboration Network website. All right, good morning everyone. Thank you for joining us today. I'm Aja Shamello. I'm the NOAA West Regional Coordinator. Today's webinar is coordinated through the NOAA Regional Collaboration Network and NOAA One Health programs. NOAA Regional Collaboration is a network of employees across NOAA connecting our work to improve NOAA service to the nation. The regional teams around the country periodically coordinate events like this, like today's webinar, to educate NOAA staff and partners about NOAA programs. I'd like to run through a few housekeeping items before we get started. The webinar today, again, will be recorded. All participants are joined in mute status, and we'll ask you to keep your cameras off during the webinar so that we can focus on the presenters and the presentation. I'll monitor questions in the questions pane on the right-hand side of your screen during the webinar, and I encourage you to add questions throughout the presentation, and we'll get to them towards the end. And right now, I'll turn it over to Morgan Szabo to tell about the NOAA One Health program. Morgan?
Thanks so much, Aja. Hi, everyone. It's a pleasure to be with you all today. My name is Morgan Szabo, and I work in NOAA's Climate Program Office and help to coordinate the NOAA One Health group. So before we get started with presentations today, I want to give you all a background about One Health and the upcoming One Health Summit. So if you're unfamiliar with the One Health concept, One Health applies a collaborative, multidisciplinary, and cross-sector approach to address potential or existing risks at the interface of human, animals, plants, and ecosystems. The One Health concept recognizes that the health of humans is inextricably linked with the health of aquatic organisms, plants, and the environment. And the work within One Health creates conditions for economic vitality and growth and supports scientifically sound, environmentally sustainable, and just practices and policies. And NOAA has a One Health team and will be hosting the first NOAA One Health Summit in Washington, D.C. from August 15th through 16th. The NOAA One Health Summit in August will bring together scientists and practitioners across the agency to connect and highlight NOAA's work on health and related issues, and with the health sector that support the One Health approach. I want to note to you all that we're accepting abstracts to participate in the summit through June 12th. That's a little less than a week away, and I will put the link to the submission in the chat. And in preparation for the One Health Summit, we're hosting a webinar to highlight a single aspect of health work being done in the 8 NOAA regions. Today's webinar is the 4th in the series and focuses on the health impacts of harmful algal blooms in the Great Lakes. And while we're highlighting this aspect of health work in the Great Lakes, please be aware that there are examples of almost every health thematic area in every region around the country. And we hope that you can join us for the webinars in the series between now and July. And of course, we hope you can join us for the One Health Summit, either in person or in DC virtually.
Thank you, Morgan. I'm excited to welcome our 2 speakers today. Dr. Reagan Errera's research focuses on phytoplankton ecology, concentrating on harmful algal species and acidification. Dr. Errera joined NOAA's Great Lakes Environmental Research Laboratory in 2019 as a research ecologist and primary investigator, where her research includes overseeing the environmental sample processor network in the Great Lakes, conducting harmful algal bloom monitoring and research activities in the region, and freshwater acidification. Dr. Stumpf leads NOAA's efforts to translate forecasts of harmful algal blooms from research to operations. He has over 30 years of experience in researching harmful algal blooms and has worked on both marine and freshwater blooms around the country. And with that, I'll turn it over to them for their presentations. Let me make you presenter. Hold on one second. Sorry about that. Just running into a little trouble. I'm sorry. I'm running into trouble with the screen sharing mode.
I got it, Aja.
Okay, thank you. Awesome. Great, thank you. Okay, and then with that, we'll turn it over to Rick and Reagan for their presentations. Again, if you have questions during the webinar, please enter them into the questions pane and we'll answer them after the discussion. Thank you.
And can I just get a thumbs up that everyone sees the slides? Or
I can.
Excellent, thank you.
Thank you.
And I'm going to turn it over to Rick.
Okay, we're going to do a tag team on this, so but only with one person driving the slides. And I will start this off. We're just capturing with the Great Lakes the work we do goes from satellites and modeling down into the water, down to nutrients, biology, and so forth. So we'll capture all of that here. We're at two different parts in NOAA. Reagan's at the Great Lakes Environmental Research Lab in OAR, and I'm in the National Ocean Service and National Centers for Coastal Ocean Science. Okay, next slide. For harmful algal blooms, what are they? The general definition is blooms that typically produce toxins that are harmful to people, animals, whether it's shellfish, domestic animals, and so forth, that they have a real risk to health in one way or the other. There are both marine blooms and freshwater blooms. We'll be talking here about freshwater because of the Great Lakes, but a very important thing is that there are, for you to understand, there are many different types of blooms. The freshwater ones are typically cyanobacteria, and the marine ones include a whole range of different species of often what are called dinoflagellates. Most of these are photosynthetic, and there's some interesting processes. They all have different factors. The marine ones often have shellfish issues, and they may cause fish kills. If people have experienced Florida red tide, there's a respiratory component with that one, but you can go to another part of the country and it'll be very different. Freshwater blooms are a risk for animals. Unfortunately, every year, several dogs in this country die from being exposed to cyanobacteria from actually drinking it. So if you get nothing else out of this, if you see scum in a lake or pond, please keep your dog out of the water. If it gets in, wash it off right away. Don't let it lick its coat off it. And there's, of course, a drinking water risk as well because it has to be treated to remove toxins. So that's a whole range. There's a lot going into it, but it's just important to understand these are different overall. So the next slide. On the coastal problem, there's indications that it has gotten worse, but we also have to say our monitoring has gotten much better. So we're finding blooms that we did not realize existed. It's not out of the question that, if you go back a few decades, or people thinking that bad hot dog ate at the beach, they might have actually ingested water with a HAB in it instead. So there are risks we weren't actually aware of at the time. So we are finding them in more places than we had previously. Some have expanded, and partially that is a climate factor. It's not just an observation. There's different, the climate parts can get complicated with temperature, but they also, that drives a whole range of physiological factors. You can ask Reagan for a lot more about that sort of thing. But it also drives overall weather factors because some of these blooms have, there are buoyancy considerations with cyanobacteria, they're swimming with dinoflagellates, and so wind patterns and turbulence also are important factors. But we have seen more, there's definitely a eutrophication issue as well, which is our middle graph. More eutrophication does tend to lead to more harmful blooms, particularly freshwater. Next slide. And just to get a sense for the freshwater blooms, the cyanobacteria harmful algal blooms, the left side shows areas of the 2,000 largest lakes in the country. This is from satellite, ones that have had detectable blooms in them. It's a satellite project that we've been quite involved with called the Cyan Project. And on the right side are from the EPA-led National Lakes Assessment. And this is showing lakes that have had toxins. These are a random sample of lakes around the country. And if they have a mark, toxins were found. Not all cyanobacteria produce toxin all the time, and that toxicity does actually vary even through the season. But if you have a risk, again, we get to buoyancy. If it floats up to scum, it concentrates it very, very intensely. And so you can actually have what might appear to be a relatively low risk in the water column become a very high risk if you have a scum form. Next slide.
Sorry about that, little technical difficulties. So I'm going to take over for a couple slides here from Rick. So just to give everyone an idea of what's going on in the Great Lakes region, as we're focusing on that today. At the Great Lakes Environmental Research Laboratory, we are a leader within the region on a number of different areas, which are kind of focused here, where we look at a number of environmental conditions across the region. Our wind, waves, and currents allow boaters and recreational individuals, as well as scientists and other stakeholders, look at how things are moving throughout the system. We consider the lakes, even though they're individual basins, at times they act as one basin flowing in and throughout each other. We also look at the ice cover and then water levels throughout the year and participate and help with that type of research. We have a regional fleet, which is mostly small boats, that is located at our field station in Muskegon, Michigan. If you come out, we'd love to get you guys out on ships if possible. We also have an issue with invasive species in the Great Lakes. You guys might have previously heard about the quagga and zebra mussels that have changed the conditions within the lakes, and as well as multiple other types of invasive species throughout the system, where we study those intensely and see how they're affecting the ecosystem within the region. And then what we're focusing on today is our harmful algal blooms within the system. So when we look at the Great Lakes, all 5 basins have harmful algal blooms that occur almost yearly. The 3 main particular areas that we focus on is the western basin of Lake Erie, which I don't know if you guys can see my cursor, but I'm going to assume that you can, which is down, okay. Rick is giving me a yes, which is down within this region of Lake Erie. It's a very shallow, warm part of the system. Within Lake Huron and Saginaw Bay is a main problem for cyanobacteria harmful algal blooms as well yearly, and we get blooms within that system. And then also within Lake Michigan and Green Bay are the 3 main systems that you may have heard of previously. More recently, we've been getting blooms within Lake Superior. However, those are more short-term blooms and they pop up quickly, as well as there have been blooms in Lake Ontario as well. So this is a reoccurring problem that we see and that we have to inform our stakeholders about yearly. I'm going to turn it back over to Rick.
Okay. 2 major uses that can be impacted by these blooms. In Lake Erie, it's drinking water. I'd say 11 million people get drinking water from Lake Erie. And then an enormous recreational and commercial fishing industry in the Great Lakes as well. Those who don't know, in 2014 in Toledo, there was actual breakthrough of toxin into the finished drinking water, and the issue was, the notice was do not drink, do not boil. That lasted for a weekend. That is, there was obviously a shortage of bottled water, huge impact on a whole range of factors, from elective surgery to restaurants, across the whole whole economy. Key factors, as I note, there's health risks to pets, and then of course to swimmers. If you don't ingest it, there's a contact dermatitis is a real risk, rashes, skin irritation if you are exposed to it. So if you do get in the water, make sure you rinse yourself off as well. But there's US EPA has defined a recreational risk for microcystins, and that's 8 parts per billion. And I'll just note that Reagan's lab had at one point measured 2,800 parts per billion up in Michigan and some of the scum. That's an enormous increase. The issue for water treatment plants is knowing when these blooms occur so they can modify their treatment appropriately. Toledo has there's been a number of changes since Toledo had theirs. Our monitoring system has increased frequency dramatically. There's more instruments in the water, more routine monitoring overall. And that particular event was a surprise, and it's unlikely that would be experienced again. But it's vital to have that alert so they can time the use, so they do not spend money on treatment they don't need to do, and they spend the money on treatment that is needed in a timely way. Next. A key factor in the blooms is eutrophication, and phosphorus load is the biggest part. Back in the 60s and 70s, Lake Erie was declared to be dead. It certainly isn't anymore, and it was a key factor between Lake Erie and the Cuyahoga River in Cleveland catching fire. Those were two key factors in getting the Clean Water Act passed. That eliminated point source effects of phosphorus, and you can see the available phosphorus metric tons going into the Western Basin Lake Erie had plummeted in the 80s as a result of implementation of proper water treatment from various sources. Unfortunately, the amount has started to increase from then, and that has to do now with non-point sources. So the concentration has gone up. Changes in farming practices have almost doubled the concentration of dissolved reactive phosphorus since the 90s to the present. And then interannual variability has to do with amount of rainfall in the spring and the resulting load bringing that phosphorus into the water. The International Joint Commission between the US and Canada and with the Great Lakes Water Quality Agreement has called for a reduction of 40% in phosphorus, which would get us back down to where we were in the 90s for loads and severity. Next slide.
So our goal for HAB research and HAB observations within the region are to really focus and enhance our overall observations, so increasing that frequency, increasing models and testing those models, and then forecasts to better inform the public. So this includes not only the scientific community, but water managers, in which Rick mentioned, that use a lot of our resources in order to make better understanding of what could be coming up the pipe to then go out to the public. And then our public stakeholders, such as recreational, commercial fishermen, and others that might be on the lakes in general using the resource. And I'm going to go to the next slide. So this kind of overview of what our program is looking at, but the big takeaway that I want to say here is that this is a large operation that includes not only NOAA and cross-line office NOAA, so featured here today is OAR and NOS, but we also work across the other line offices of NOAA in order to get a lot of this work done, and cross-agency. So we work with EPA in particular, as well as other agencies within the federal government. We work with state agencies, and then we also work with our university partners. So this is a very large operation in which we tap into many different partners in order to get a lot of these observations done and across the board. But our main focus is these major areas. So satellite imaging, which is Rick is going to go into a little bit more in depth, and then advanced modeling and forecasting. We do monitoring and real-time buoys, which I'm going to talk about a little bit, and our hyperspectral imaging, which is right now plane-based, but we're developing that into uncrewed systems as well. We use other autonomous systems within the water itself, and that is with our partners at Ambari. And then last but not least, we do a lot of experiments. So to test out not only what's going on in the field, but also what we're seeing back in the lab. We're taking that back out in the field and seeing how those react together. And that all together kind of correlates or kind of comes together to how we are considering blooms, understanding blooms, and then providing better information out to our stakeholders within the region. I'm going to turn it back over to Rick.
Okay. So we'll go through those different parts that Reagan captured, a little bit about each one and what we're doing. Satellite data is one of our key monitoring tools, provides that overview, that synoptic view of what's happening. And about with the satellites we're using, the Copernicus Sentinel-3 is our primary one. It was it's run by EUMETSAT, European Union. And we get about 5 or 6 images a day. It does need to be cloud free. We cannot see through clouds. But in the summer when the blooms occur, that is pretty common. Example on here is you see a sort of a typical true color of an intense bloom. And this satellite has specific wavelengths that allow us to target cyanobacteria specifically. So we can distinguish cyanobacteria from what would be good algae, diatoms, and so forth, and also distinguish it from things like sediment as well. So we're able to have concentration fields. And this is used for both shorter term and long term analyses. Climatologies, we have over 20 years now of a climatology. And if we go to the next slide, we use it to actually pull into our overall bulletin system and forecast system. We provide imagery. There's a 5-day forecasted surface pattern from a model. And we also forecast mixing. Mixing, if you don't have any mixing, it tends to produce a scum in the surface, which is bad for boaters and recreation. If it mixes a lot, it ends up with a bloom down where the water intakes are. So we have different customers depending on what's happening for the mixing. We also use the reports of toxins from the field program to provide that information as well on potential toxicity. And people can upload a PDF file. So you can click on that link. There's also a short reference on the bottom, gousa.gov down there. Next, example of the actual forecast. So we pull in the Lake Erie operational forecast system model, and then we bring in the satellite data, and we have a 3-dimensional biological model that we include to allow us to move the bloom around and capture where it is in the water. The arrows in this case show the actual transport. Major source of water is the Maumee River near Toledo, of phosphorus, of nutrients. The Detroit River is the largest flow into Lake Erie, but it is a very low nutrient load. So it generally doesn't drive these blooms. But you can see how much movement there is going on with these blooms over the short time, over this. Next slide. We are now working with we've been testing with our partners in the universities as well on a toxin forecast where we take into account the combination of field data on toxin and the satellite data on the bloom concentration and put those together to a predicted toxin level risk. We're in the process of testing this model out, and we hope to have that included within another year or so. Important thing with this is it's that the concentration varies. The concentration of toxins vary with the bloom intensity, but it varies over time. And so it's really critical to capture this so that we're getting the right toxin information to people. I also have to say, from satellites, we can see pigments, and the toxin is not a pigment. We cannot detect toxin from satellite. You absolutely have to have the field data in order to put this together in the field models. Okay. Next. On the mixing side, as I said, we have a 3-dimensional model, and a series of experiments were done that identified the amount of buoyancy with the bloom as it goes up and down in the water. Just as a concept here, it's there's more light at the surface, and what happens is the cyanobacteria, they photosynthesize, they carbo-load, they get heavy, they sink, and then they have an opportunity to get additional nutrients. They use up some of the carbohydrates, and they have these vesicles that hold CO2. And when those fill, they float back up to the surface and potentially repeat the process. So you end up with this fluctuation potentially through the day, and that just depends on the bloom. How much the winds are determines the mixing, as we know, and we can model this over time so we can capture variations over a few hours between day and night, and also from over several days out. Next. And the applications are good for a number of purposes. Here we're noting locations of parks and water intakes around Western Lake Erie. And as you can see in this particular case, the bloom is impacting a couple of the intakes, which are little white areas. It's actually near Toledo, but some of the ones out near the islands are not at risk right now. Before we started this, pretty much if there was a bloom at Toledo, everybody started treating. And now they have the information to not be surprised and not treat earlier than they need to as well. So next slide. And with the imagery, we have gone to, we have a 20-year time series, which has allowed us to do modeling for, or just reporting how severe the blooms have been in different years. And you can see these variations over time. 2015 and 2011 had the wettest springs. We have seen the highest phosphorus load in the springtime, which has led to this intense blooms. But here we can see the examples of each year of the most intense bloom. 2011, 15 were quite severe. And how much they vary. 2011 actually went out past Cleveland because there was a late season wind event while the bloom persisted. Whereas in some other years, it's quite intense and stays right in the basin like 2013 and 2017. But we get an idea of the overall severity of these blooms. And we report those numbers out each year. Next. So we do a seasonal forecast, and that will be on June 29th this year. We work with the Ohio Sea Grant to do the forecast, and we include, right now we're actually doing initial forecasts. We have to use models for the river forecast going into the end of July. So there's a little more uncertainty about that. And then we assemble a number of models and put those together. Example forecast, this is actually our most recent early season forecast, which we're looking at a bloom somewhere between low and moderate. And that uncertainty has to do with trying to forecast how much rain there will be from late June into July. And some of you may have heard there's an El Nino developing, and that affects rainfall, but it doesn't produce it, but affects it. And we're dealing with a complication of a dry spring and a something that disturbs the weather. So we're looking in 3 weeks that we should have a much better perspective of what that impact is. And that is also, it's a webinar as well. If we should have the link here, but you can get that from Ohio Sea Grant if you wish to sign up for that. Next. And on toxin, we'll note why it's so important to actually measure toxin. In 2014, when Toledo had the problem, the bloom started off quite toxic, and we're trying to understand those factors as well. In contrast, 2015, which had a very overall a severe bloom, the toxin level was much lower. You can see about 1/4 of that. And so getting the toxicity right when the bloom starts as compared to after is really critical. And that toxin data, that's the sort of thing, Reagan's labs collect that data. They turn that around within a day, pretty much, of the cruise. So we have that information right away, and it's really invaluable. You can see how much it actually changes as we go through the season. So early in the season, it's always more toxic, and then it drops off. And that's a key factor to try to get out of these models. Next, I think this goes back to you, Reagan.
It does. Thank you. Oh, and I went too far. So as Rick mentioned, we go out and sample the water. There's nothing better than going out on Lake Erie and grabbing some water and bringing it back to the lab for processing. We do discrete sampling starting actually in April, and these are pre-bloom samples that we're trying to capture so that we can look at the succession of how the bloom setup, including not only the phytoplankton within the system, but also the environmental conditions. And we're listed here on the left the discrete samples and what we're taking. So in April, we measure in April and May, just once that month. In June, currently we're measuring every other week. And then starting in July, we measure weekly all the way through to the end of the bloom, which is typically in October. However, that has seemed to be getting later and later in recent years. We also have continuous systems out in the lake when buoys and sensors that are taking additional data for us that we can then kind of pair together with that discrete sampling. For the discrete sampling, we actually have 8 different sites in which we cover, and from the maps previously that Rick showed, it kind of covers where the really intense portion of the bloom is located. And you can find that information from our website here, and then also GLOS picks that up as well. So from our weekly sampling, we can start to get at how successional change happens within the ecosystem. So how the phytoplankton are shifting from a diatom-dominated community to a cyanobacteria community. And as that shifts over to a cyanobacteria community, we see a shift in the toxins, or the presence of the toxins show up within the system. So in the map over to the right, hopefully you guys are seeing little bubbles pop up and down in different colors and sizes. And that just indicates the change in toxin over a 6-year period that we are seeing. And the size of the bubble is actually showing how toxic it is. So this is a really coarse look at how the toxin is changing over the course of the bloom. And hopefully you're also noticing with those little bubbles as they pop up that it goes from non-toxic in those earlier months to really toxic really quick. And then it backs back off as the bloom develops. So we never quite know. We know certain things about when the toxin is going to be at its highest level, but we don't know when that might shift or when that's occurring. So that's why a lot of this environmental conditions and our research is helping explore those types of ups and downs within the bloom itself. With the continuous buoys, we can put that together with the discrete samples to get a better understanding of how the environmental conditions might be shifting and then impacting what we are seeing within the phytoplankton bloom succession. So that's what I'm showing here. This is at our WE2 site, which is close to the Maumee River, right as it comes out and within the basin. And we have there located, or at that site located, one of the continuous buoys, and we're representing SRP, sorry, excuse me, here in the black line or the gray line, and then the chlorophyll A and what phytoplankton group is associated with that. And as we lay that over, we can see that as SRP decreases, that's typically when we see that shift over from the diatom-dominated community to that cyanobacteria-dominated community within the system. However, a coarse look is great, and weekly samples does get us a really good idea of what's going on within the system. But to better understand the system, one of our goals is to increase the amount of data that we're getting and observations we're getting out of the system. And one of the ways that we're doing that is using emerging and advanced technologies. So one of the systems that we use here at GLERL is the environmental sample processor, and this is was developed by Mbari, or our colleagues out at Mbari, and is now commercially available. We have 3 of these systems within the lab, and what they do, or what their term does, is a lab in a can, in that they will do the analytical processing that we can do in the lab actually in situ in the field. So you can see the inner parts of an ESP located here with my colleague Dana working on it. Within the ESP, our colleagues at NOS, NCOS, have developed an assay, and similar to the ELISA assay, to test for toxin that we put within the system, and then we can get what we call near real-time toxin analysis back. Basically, within 2 hours of water collection, we get a rough estimate of what the toxin is doing out in the field. We can take up to roughly about 40 samples, and that all just depends on negatives and positives that we have to use within the system for each deployment. As I mentioned, we have 3 of these systems that we deploy yearly, and you can see the locations in which we deploy them. And I'm going to show a little map on the next page too. So we have 2 main locations in which we deploy this. One on the Ohio side, which is our ESP1 station, and then another one over on the Michigan side, which is the ESP2. The ESP sits in this blue lander on the bottom of the lake, and that allows us to actually take samples at 2 depths and 2 different locations, or 2 depth locations. One at the bottom, which is where the water intake actually draws the water from, and then at the surface where scums and other recreational individuals can get in contact with that toxin. So when the ESP is out, it's taking its sample, it's returning the information. After it's complete, one of the reasons we have 3 of these systems in-house is that we can pull one system out and drop a system on it when we're pulling the other one out, so we never lose data, that we can have a continuous system going throughout the entire bloom season. This is what some of the data looks like. So this is in 2017 and 18, we only had one instrument out at a time. So you can see lags within our data. And we also could only take samples about every other day to try to increase the amount of data that we were getting out. But now that we have three, we can get a much more fine-tuned and in-depth look at the toxin and how it progresses over the course of the bloom, such as in 2019, where we're taking samples every day and switching those systems out. So the beauty of that is really seeing this up and down of how toxin changes, not only during where in the water column, as Rick mentioned, the bloom is moving throughout the water column and therefore the toxin is moving throughout the water column, but also how it changes over the course of the bloom. As in the 2019 data, you can see that the bloom went non-toxic or very low toxin later, roughly about September, and then stayed non-toxic. But in 2017, that wasn't the same thing that we saw, in that the bloom went non-toxic and then it almost hiccuped again and went toxic towards the later portion of the bloom period. So having instruments out in the field and providing this data allows us to provide that back to the public and our stakeholders to allow them to know where we are with the toxicity of the bloom. So as I mentioned, we put these ESPs out in strategic locations within the lake. However, if you've ever seen Lake Erie during a bloom, it kind of looks like this, which is very, very patchy. The bloom is not one consistent bloom. It's got pockets and whatnot. So it would be great, while these locations are wonderful, it'd be great to be able to move throughout the bloom and be able to get the same information and data. Well, luckily, our colleagues at Mbari have thought of that as well and have actually shrunk the ESP. So the lander type is the second generation ESP, shrunk it down to make the third generation environmental sample processor that fits within these long range AUVs that we can then deploy and can move throughout the bloom. One of these, the one in the farther back, is actually one equipped with the ESP, and the one that's closer is what we call a sentinel device, in that we send that out to find high areas of chlorophyll in order to then go sample from. So this is what the third generation ESP looks like. It's more of a wheel that moves around. It actually allows us to take more samples. So from that, we get not only toxin information through an SRP, again, developed with our colleagues at Mbari and NOS to develop that assay, but also we get genetic information. So we not only get genetic, but transcriptomes. So we get both genes and RNA out of these archival cartridges. And you can see here of them just kind of putting it together. And I don't know if that video will play, but it's basically putting it in to the ESP itself. So this, or the long range AUV. So this is the assembly of the long range, and you can see the two systems next to each other, and the 2G in the back on the right-hand side, and then the 3G up out front. We've deployed these in 2018, 19, and then 2021, and we'll be doing a deployment again this summer, however, slightly tweaked, which I'll get into in just a second. So some of the other emerging technologies in which we are using are hyperspectral imagers. So this is run by Andrea Vanderwood out of our lab, Chloral, here in the Great Lakes. And they put these right now currently on planes, into our small plane systems that go out and help us map the bloom underneath those clouds. So as Rick mentioned, we get a lot of cloudy days. Sometimes we can get out at times that the satellite can't get under and provide information to the water managers about where the location of the bloom is. But we are also testing this on uncrewed systems, of switching from a plane-based hyperspectral system to a more drone-based system. And this is taking advantage of the new technology that's coming out to be able to do shore-based type flyovers to see where the real intense areas of the bloom might be. Now, as Rick mentioned, that doesn't necessarily mean it's toxic. So it means we need to pair it with something that, or information that provides the toxicity out to the public as well. And I'll get to that here in a second. So when we pair not only the 3G ESP with this hyperspectral mapping, what we can do is really get an intense look at the bloom itself, moving throughout the bloom, seeing where maybe hot pockets are within the bloom of not only chlorophyll, but also that toxin, and make those comparisons across the board. And the map on the far right shows that the long-range AUV not only moving throughout the water column as well, and taking samples throughout with the mapping overlaid. But a long-range AUV is great to a point. So that, as I mentioned before, the western basin of Lake Erie is shallow, which causes some problems for these wonderful instruments. It might not be the best tool for what we have. So this summer, we're going to be testing the 3G ESP in a surface vehicle instead. Again, working with our partners at MBARI and NOS, we're going to put that 3G inside the surface vehicle and then try to monitor the bloom throughout, again, autonomously from shore. And that's just a video of it testing, or it's driving around Lake Erie. So hopefully, to wrap kind of this up and allow plenty of time for questions, Rick and I hopefully have provided a good overview that we employ multiple different techniques in order to study this bloom and to provide up-to-date and accurate data to our stakeholders, mainly the public, that is not only out in the water, but also consuming the water within the system. I like to make a play that Lake Erie is a wonderful test bed. We have tested many advanced technologies and emerging technologies, as well as monitoring systems. As I mentioned previously, this really takes a large effort to pull this all together, and then it's a great way to test new ways in order to then move it into other areas that may be affected by harmful algal blooms. The surface vehicle, for instance, we are testing in Lake Erie, but we hope to then test it and move it to places like Lake Pontchartrain and the Mississippi coast for their cyanobacteria blooms that are plaguing that system as well. So this is a great place to first test it and then move on. We're also using a wide range of different systems or different ways in order to explore the bloom to get a fuller understanding and fuller information that we can then provide to the public through both the forecasting and the toxicity, but also using things like omics and looking at plume ecology throughout the system. And I'm not going to read the list. You guys can do that. And that's kind of all we kind of came up with or pulled together for you guys today. We hope it was thought-provoking and that you guys have some questions and also gives you some reason to come out to the Great Lakes and experiencing them yourselves. So I'll turn it back over to
Thank you so much. And thank you for the invitations too. We'll take you up on that. We got a lot of audience questions during your presentation, so I appreciate that. And so I'll actually just go through them because they're really great ones. So the first one is, there are hundreds of small lakes throughout Michigan. How can the average Joe tell if there's a harmful algal bloom in the smaller lakes that might be subject to monitoring?
Rick, do you want to take that with the Cyan project, or?
Well, we could start. Why don't you start with the basic field, and I'll talk about what we're going to try to do next.
Okay. So the best way to determine if you have a cyanobacteria bloom is it green? So if it's green, definitely be cautious. Obviously, duckweed is also green, and it's not toxic. It's a natural part of the system. These guys are natural part of the systems. They've just got.
There are little leaves on duckweed. Yeah, you can tell.
Yeah, they're little leaves.
Actually, little leaves.
Yeah, this more looks like paint. Is the best way to put it. In that, like, if you dipped something in there, it would look like you're pulling out a thing of green paint that's coming out. So because you can't tell just by looking if it's toxic or not, we advise that if you see green color, do not go into it because of, we can't tell just because it's green if it's toxic. Now, projects are looking at those smaller lakes, which is, I'm assuming, where I'm going to pass it on over, and Rick can talk more about those smaller lakes and what's going on.
So for the larger ones, the Cyan project, which you can find at EPA Cyan or also NASA as well, where the data is distributed, does about 2,000 largest lakes in the country. In Michigan, there's probably, I'm not sure the number, but I'm sure there's 100 or 200 lakes, which leaves for a number of several thousand, I realize, there. We're in the process now of looking at a higher resolution satellite that would not have quite the frequency, but at least provide that information. And so we've just started a preliminary project going across a number of agencies, and hope in a couple of years that we'll be able to actually do pretty much all the lakes that people would be interested in the country. So that's the goal in a few years. So in the meantime, yes, you look for green paint, or check for the larger lakes, the status from Science. And there is an app, by the way. There's a mobile app, so you can actually, if we can pick it up on there, you can actually get an assessment at your phone.
Great, thank
And
you.
I would
Maybe
also,
go ahead.
sorry. I was just going to mention the local health advisors. So a lot of the states will go out and monitor those smaller lakes. So definitely check your local
County or state health departments. Yeah.
Yep. Sorry, go ahead.
Thank you. Yeah, and I'll try to grab that mobile app link for you and send it out when we send out the wrap up from this afterwards. So another question, you said at some point during the presentation, I think Rick said it, that the Detroit River is a low nutrient source, and the person in the audience was surprised to hear that and asked for some elaboration.
If you're talking sheer quantity of phosphorus, it certainly provides a lot. The key thing is the concentration is low. And cyanobacteria grow, they do not grow well, they do not compete well in water with low concentrations of phosphorus. They definitely like a high concentration. So it's, the simple example is if you put a cup of sugar in your cup of tea versus a teaspoon in your cup of tea, that's the difference. So the Detroit River is not a good source for the cyanobacteria blooms. I don't know if you have anything else to add to that, Reagan.
It definitely is not, it has nutrients in it, but not at the sheer volume, as Rick mentioned, as the mommy or concentration.
Great, thank you. So the next question regarding the percentage contribution of different phytoplankton groups to the total, how is that determined? And so the questioner asked, was it cell count or pigment analysis?
So that was the graph that I showed was pigment analysis. So that's actually using a flora probe, which we've calibrated kind of here in the lab to pick out the cyanos within our system, as well as diatoms that are local to the system. So whenever we go out in the field, we dunk a flora probe and get a profile, but we also look at it at the surface. And this year we will be deploying several flora probes out on some of our buoys as well.
Great, thank you. And I'll keep flipping through because we've a good number of questions and enough time, I think, to get through all of them. You guys mentioned omics and uncrewed systems, a lot of the science and technology focus areas. A question came in about machine learning, but then I'm also curious about, citizen science in monitoring. So yeah, both of those other focus areas, how do you use those with this?
So some of the machine learning that we're doing with some of the omics techniques, just with development of pipelines and things along those lines. I'm trying to think of what else. We don't take imaging right now. We are in the process of testing different imagers that machine learning really does well with and has been developed for. But cyanobacteria can be single cell, which is really then small. It's about 3 microns big, or it can be a colony that is multiple microns big. And part of that problem then is that typical imagers, such as the imaging flow cytobot or the flow cam, sometimes gets clogged, and we can't get as easy of an image that way. So it takes a little bit more finessing. So we are in the process with other colleagues of testing different types of imagers so that we can apply things like AI to the systems. Rick, have you been involved in some of the citizen science stuff? I know there's been collection sites and the little microscopes to check to see if it's microcystis.
In other areas, we've been working some with citizen science. Not a lot up in Lake Erie. I mean, we have a pretty good system here for monitoring between what we have. I think the citizen science, probably the real power there is going back to the earlier question of all those small lakes in Michigan, that there are potential, there's a few groups that are starting to look at citizen science just to get more information in, and that has a real promise to try to capture that.
Great, thank you. Okay, this is a question on the ESPs. What are the depth limitations for the 3rd generation, and how are other surface autonomous vehicles helping with those limitations?
So the depth really depends on what instrument it's in. So the long range AUV can go very deep if the 3G ESP is inside of it and housed. So it just depends on the vessel in which it's placed. So for the surface vehicle that I mentioned that we'll be testing out later this year, one of the goals is to be able to sample on multiple depths with that, and that will be determinant upon the depth of the lake itself. So it just kind of depends. I know out on the West Coast where they've used the 3G ESP before, and even in places like Lake Michigan, in the middle of Lake Michigan, they've gone down pretty deep with those long ranges versus the surface vehicle. For other surface vehicles thus far, this will be the first time we're testing a surface vehicle based operation for GLERL. We have other AUVs in which we use for different projects in different ways. So we have one that we're testing right now to go under the ice, and that's Steve Ruberg is working on that within the lab to get some of that information that when we can't get out during the winter and we're ice covered, trying to get some of that information back of what's going on within the ecosystem. As well as we have a really unique karst system up in Lake Huron, which has unique algal formations and bacteria mats, which we have used autonomous systems to go down and sample as well. So there's a whole list, but I would probably direct you directly to Steve Ruberg, because he's going to be able to provide you the best information along all the different autonomous systems we have used.
Great, yeah, and that there's a commenter who's asked also about how well those systems work in shallow turbid lakes, so maybe that's the direction as well as to Steve.
Yeah, so yeah, the long range AUV, that we did have a problem where it got stuck a few times. Then that's why we're now testing the surface vehicle. The surface vehicle thus far has, without the 3G in it, we tested it last summer. It worked very well within the surface or in the shallow areas. It can get into as shallow as a half of a meter. So it's done rather well within that system. Now, the next test is let's put the technology inside and see how well it does. So check back with me in September and I'll let you know.
Great. And then another question about, transporting these technologies out of the Great Lakes into other areas. So the timeline to bringing those technologies to other large lakes in the Gulf of Mexico and adjacent regions.
Yeah, so our plan for that particular project, this was NCOS funded project, PCM-HAM, and specifically, if anyone knows about that program, it is to test it next year, potentially in Lake Pontchartrain, but most likely we're going to have to push that back a year to what would that be, 25, where we'll be testing it in Lake Pontchartrain. These systems have also been used by HUI, so the C-Track system at least. Other systems are being tested as well. I know on the West Coast they are testing another type of autonomous system that can deal with deeper water, and also I believe not using the 3G, but maybe using the 3G, but I don't want to talk out of turn. This is an IUCE funded project. Tiffany Vance would be the best person to talk to about that project out there using a surface vehicle along the West Coast.
Great.
I'll just add separate. Yeah. The Cyan project provides data, but not necessarily analysis. And we have transferred some of these to some other places with critical blooms where we I put a link in where it's not only the presence of the bloom, but also, for example, how large the area it is, coverage, some other information. So people get a perspective in some of those areas that are critical. We're not doing this across the whole country, but in places that have been identified as having critical blooms.
Great. And then I'll leave you with one last question. How might changes in climate impact cyanobacteria blooms, especially in the Great Lakes?
I'll steal something from a colleague that cyanos like it hot. So they typically do better when water temperatures are higher and they can outcompete other phytoplankton types. So that's one aspect that we are seeing with climate, or potentially see with climate. In addition, we have the increase of carbon dioxide, not only within the atmosphere, but within the water. If anyone remembers back to basic biology, phytoplankton needs CO2 in order to photosynthesize, and the increase in the availability of CO2 could potentially impact the bloom. And that is work that is currently being looked at our lab and at other labs in order to see how CO2 might be impacting the bloom, or focused on the bloom. Cyanobacteria are very efficient at capturing carbon dioxide. So that also bodes well for them under future climate conditions. Rick,
I'll add another side. On the hot, that could mean start earlier, last later. But wind also matters for these that are scum formers. They're optimized for calmer conditions. And so changes in wind patterns have a potential of altering those blooms as well, because they can either disrupt them or make conditions far more favorable. So it's not only temperature. Climate change does involve weather patterns as well.
And speaking of that, that's going to change runoff patterns, which could increase the nutrients flowing in. So we could go on this forever. And I should also say another colleague has also said that they like it cold too. Some of our research and experiments out of this lab have also shown that cyanobacteria just do also enjoy the cold water temperatures as well. So
different species.
Yes, different species.
Yeah, precipitation, that's an obvious one, which disruptions and changes in rainfall or in intensity, because very high intensity rainfall events can cause more runoff than low intensity events. So you can get different loading factors. Yeah, can go for quite a while.
Yeah. Well, great. With that, thank you guys so much for the fascinating presentation today and for answering all of those questions. I want to thank everybody for joining us and encourage you to look out for announcements for our future webinars in the One Health series. We have a small pause in our webinar programming until June 29th, and we'll head virtually to the Atlantic Coast to talk about extreme heat then. So with that, thank you everyone, and we'll see you soon.
Thank you.
Bye.